Welcome to Sri Learning Academy. Let's simplify issues in multi-threading. Imagine you are in a busy kitchen during peak hours. Multiple chefs are chopping, stirring, baking, and plating at the same time. Everyone is skilled, everyone knows their job, but the moment coordination slips, things can go very wrong. Salt gets added twice, dishes get stuck waiting, or one chef never gets a chance to use the stove. This is very similar to what happens inside a computer when multiple threads run at the same time. Multithreading gives us speed and responsiveness, but it also introduces some serious challenges. That is exactly where issues like race conditions, deadlocks, and starvation come into play. When we use multithreading, we allow different parts of a program to run concurrently. Threads often share resources such as memory, files, or variables. This sharing is powerful, but it is also risky. One small mistake in coordination can cause unpredictable behavior. The system might still run, but the output can be wrong, slow, or completely stuck. Let us start with race conditions, because this is usually the first problem developers face when working with threads. A race condition happens when multiple threads try to access and modify shared data at the same time, and the final result depends on the timing of their execution. The word race is very important here. Threads are literally racing against each other to read or write data. Consider a simple example. Imagine a shared variable called balance that stores the money in a bank account. Two threads are running at the same time. One thread is depositing 100 units and another thread is withdrawing 50 units. Both threads read the current balance, modify it, and write it back. Now imagine the balance is 1000 initially. The deposit thread reads 1000 and plans to write back 1100. At the same time, the withdrawal thread also reads 1000 and plans to write back 950. If the withdrawal thread writes last, the final balance becomes 950 and the deposit is completely lost. No error message appears, but the result is wrong. This is a classic race condition. The dangerous part about race conditions is that they do not always happen. You might run the same program 10 times and see correct results. And on the 11th run, something breaks. This makes race conditions very hard to debug. The root cause is that threads are not synchronized properly when accessing critical shared data. Later, when we talk deeply about critical sections, mutexes, and semaphores, you will see how operating systems and programmers solve this problem. For now, it is enough to understand that race conditions arise because multiple threads act on shared data without coordination. Now let us move to deadlocks, which are even more dramatic. A deadlock happens when two or more threads are waiting for each other forever. Each thread holds a resource and waits for another resource that is held by someone else. As a result, no one can move forward. Think about two people trying to cross a narrow bridge from opposite sides. Both step onto the bridge and stop, waiting for the other to move back. Neither wants to give up their position. They are both stuck, and the bridge is blocked. This is exactly how a deadlock works in a multi-threaded system. Here is a simple technical example. Thread A locks resource X and then tries to lock resource Y. At the same time, thread B locks resource Y and then tries to lock resource X. Thread A will not release X until it gets Y, and thread B will not release Y until it gets X. Both threads are waiting, and neither can proceed. The CPU might still be running, but these threads are frozen in place. Deadlocks are not limited to just two threads. They can involve many threads and many resources, making them even harder to detect. What makes deadlocks especially dangerous is that the program does not crash. It simply stops making progress. From the outside, the application looks like it is hanging. Operating systems study deadlocks in great detail, which is why there is an entire module dedicated to them later in the course. Concepts like necessary conditions for deadlock, resource allocation graphs, prevention, avoidance, and detection all build on this basic idea. For now, remember that deadlocks are about circular waiting. Everyone is waiting, and no one is willing or able to move first. Next comes starvation, which is a bit more subtle and often misunderstood. Starvation happens when a thread never gets access to the resources it needs to run, even though the system is still active. Unlike deadlock, where threads are stuck waiting for each other, starvation happens because the system keeps favoring some threads over others. Imagine a ticket counter where priority customers are always served first. Normal customers are told to wait. If priority customers keep arriving continuously, normal customers may wait forever. The counter is working, people are being served, but some individuals are being ignored indefinitely. That is starvation. In a multi-threaded system, starvation often occurs due to scheduling policies or poor synchronization design. For example, if a high priority thread constantly preempts low priority threads, the low priority threads may never get CPU time. They are ready to run, but the scheduler never selects them. This is called starvation due to priority scheduling. Starvation can also happen with locks. Suppose a thread needs a lock to enter a critical section, but other threads keep acquiring and releasing that lock faster. The unlucky thread keeps waiting and never gets its turn. Again, the system is not stuck, but fairness is lost. One important difference to note is that starvation can sometimes be resolved automatically if system conditions change, while deadlocks usually require intervention. Still, starvation is a serious problem because it leads to poor performance and unpredictable behavior, especially in real time and interactive systems. When you look at race conditions, deadlocks, and starvation together, a common theme appears. They are all problems of coordination and resource sharing. Multi-threading makes programs faster and more responsive, but it also forces us to think carefully about how threads interact. Without proper synchronization, threads interfere with each other. With too much synchronization or poor ordering, threads block each other. With unfair scheduling, some threads never get a chance to run. This is why operating systems provide synchronization tools and scheduling strategies, which you will study in detail in the upcoming modules. Concepts like mutex, locks, semaphores, monitors, condition variables, and atomic operations exist mainly to prevent these issues. Similarly, scheduling algorithms try to balance performance and fairness to reduce starvation. In simple terms, multi-threading is like teamwork. When everyone communicates clearly and follows rules, work gets done faster. When communication breaks down or rules are unfair, chaos follows. Race conditions corrupt data, deadlocks freeze progress, and starvation quietly sidelines some threads forever. Understanding these issues is a crucial step toward writing correct, efficient, and reliable multi-threaded programs. That is it for this video. See you in the next one.